Alright, hi everybody. So this is thermodynamics kind of part 2. So in the beginning of the year we did some thermodynamics where we talked about the first law of thermodynamics, which is essentially heat conservation and energy conservation. And what we were saying in that particular chapter was that the energy of the universe is constant. It's not changing. And we saw this when we would do heat problems, where we would have the delta H of the system would be equal to the opposite delta H of the surroundings, or MCAT equals negative MCAT. So if, for example, you were to put a bar of hot copper into some cool water, there would be this transfer of heat between the two without any energy loss. We also saw this with Hess's law, where we would do products minus reactants in terms of heat, or with bond energy, bonds broken minus bonds formed. But the thing is that this doesn't tell us anything about how a reaction would occur spontaneously. And by spontaneously, I mean if the reaction will ever occur or not. And that's what we use a new term, which you've heard before, called entropy, to determine if a reaction is actually going to occur in a spontaneous way. Now the AP has sort of moved away from this term spontaneous, and they kind of have replaced it with what they call thermodynamically favorable. So now spontaneous, as we see it here, that is actually being replaced by something called thermodynamic favorability. You know, the idea is that when people think of spontaneous, they think of their friend who's gonna, spontaneously, cut school or something like that. But here we have this situation where, will the reaction occur? If it occurs spontaneously, it may be in 10 seconds, it may be in an hour. There's no real sort of connection with time, and the term spontaneous sort of gives us this sense that it's happening quickly. Instead, if we say thermodynamically favorable, that's kind of talking about, well, will it occur? Are the conditions favorable in terms of the entropy change and the enthalpy change that will cause the reaction to actually happen without any outside help? So when we think about entropy, the qualitative definition that we get is disorder, chaos, randomness. But we'll talk about a more quantitative definition in a little bit. Now they give the symbol S for entropy, and notice it's not delta S just yet. But we will have changes in entropy. We will do delta S. But the thing with entropy is that it's an absolute value. It's not measured by its change. So for elements like oxygen, that actually has an amount of entropy associated with it, because there's a certain amount of disorder or randomness that's associated with it. Here's an example for you where we have, a deck of cards, and we can say, well, they can be arranged in 52 ways. And that's quite a number of combinations, 10 to the 68 combinations of cards if you were to have a deck of 52 cards. And that's pretty disordered in a sense, yet if we were to take those 52 cards and then just throw them and scatter them on the floor, now we'll have so many more different possible arrangements, and the entropy will increase exponentially, even from the original myriad ways that you could actually arrange the cards in the deck. Now, we also can look at entropy quantitatively. But I have to say that, like, the AP isn't really going to test you, or the IB at all for that matter, on, this sort of quantitative measure of entropy. But I get the question a lot, what is entropy? How is it measured? And so Boltzmann came up with this idea that entropy, which is S, is equivalent to this constant K times the natural log of W, and W is the ways that you can arrange the particles. So, the more ways that you can arrange the particles, because K is a constant anyway, the more disorder that you'll have. We can also think of entropy as a state function that depends only on the final and initial conditions. And just like we did delta H, we can also do delta S, where we do the entropy of the final state minus the initial state will give us the change in entropy. This is generally done for the system, not the surroundings. Now, we apply entropy in the second law of thermodynamics and the third law of thermodynamics. The second law of thermodynamics again talks about spontaneous reactions and the idea that if you have a reaction and the entropy of the universe, notice I capitalized that one, is increasing, the reaction will occur spontaneously. So as long as the entropy of the universe is greater than 0, then you will have a reaction that will occur without any outside help. You put the reactants together and they'll react. It may take, a minute or a day or an hour or a year, but eventually those reactants will react and form products without any outside intervention. The way we can look at this mathematically down here is that the change in entropy of the universe, just like the change in energy of the universe, is equal to the change in entropy of the system and the surroundings. The system, again, is your chemical reaction. The surroundings is everything else. Those two together should be greater than 0 for the reaction to occur spontaneously. Now, something that's interesting about entropy is that it also relates to this third law of thermodynamics. And so the third law of thermodynamics says that if you're at absolute 0, the entropy of the system is 0. And that's because at absolute 0, things could only be arranged perfectly in one particular arrangement. And that particular arrangement would be the natural log of one particular arrangement, that would be 0. And so the entropy would be 0 of the system. Now this is why when you look on like a thermodynamics table for reference, you'll see that entropy isn't delta S, it's actual S. And that's because it's compared to this 0 state where you're at absolute 0 and the entropy of the system is 0. So when we look at thermodynamic tables, you'll see that those thermodynamic tables, they don't have delta S, they just have S. If you want to find delta S, you'd have to subtract the products from the reactants, or be given the value for delta S in a problem. Now, when we talk about standard molar entropies, we're always talking about the same conditions that we were using on table C when we did the other chapter, chapter 5, which was the first law of thermodynamics. And that is, we'll be dealing with 1 molar concentrations, we'll be dealing with 1 atmosphere of pressure if you're a gas, and we'll also be dealing with 298 Kelvin. I want you to also notice something that's important about entropy units, and that is that it's joules per mole Kelvin. When we talk about enthalpy, delta H is in kilojoules per mole. So the kilojoules versus the joules, when we start talking about free energy and we put these two values, delta S and delta H, into the same equation, we have to match up their units. So you can either change delta H to joules per mole, or you can change delta S to kilojoules per mole Kelvin. Now, in general terms, and the AP likes to ask about this, when does entropy increase? They'll give you a reaction and they'll say, is the entropy of the reaction increasing or decreasing? Well, entropy is going to increase if you have a temperature increase. As the particles move faster, there's more randomness. When you go from solid that's highly ordered to liquid, to aqueous, to gas, then the solution becomes more disordered and there's more possibilities for different arrangements. When you dissolve ionic solids in water, generally they become more entropic. There are some exceptions. Sometimes the water will surround the ions, and when they surround the ions, they'll actually make these ordered hydration shells that will decrease the entropy. I've seen a rare question here or there and that on the AP exam, so you should be aware that that's a possibility. As you go down a group, the atoms get bigger, more electrons, more possibility for the arrangements and places for those electrons to be. If you have graphite versus diamond, graphite, the atoms are arranged in sheets, the electrons are free to move, there's more movement, there's more entropy. If you increase complexity, so you have something that has more particles, it will also end up having more entropy. When does entropy decrease? All the opposite kind of things. Something that's important is when if you have a reaction and you make less moles of gas, well, in that case, you'll also decrease entropy. So in this video, I've introduced what entropy is and how it works, and we can close with a simple calculation. If I were to give you something like combusting propane in oxygen, so C3H8 plus O2 yields CO2 plus H2O, and they tell you that liquid water is formed. So if you look in table C, or you go online and you look up any thermodynamics table, what I'd like you to do is, I'd like you to, as a review, find delta H actually for this reaction, and I'd also like you to find delta S for this reaction. I will post table C again. It should be in the thermodynamics chapter. If it's not, I'll post it again for this chapter. And I might just post it with this video so that you have it in iTunes U, and you can do this. Or you could just look online if you type in thermodynamics table. These are pretty common compounds and elements, and they'll come up right away. So let's do these two and see what we get. And then in class, we'll talk about, what this looks like. And we'll try and, see if this actually works where, what we could do is we could do a prediction. So why don't we do that too? Let's predict. Let's do this first. Predict delta H and delta S. Once you predict delta H and delta S, then actually calculate it. And let's see how they match up. All right, thanks so much for watching.